Nobody on the road, nobody on the beach. I feel it in the air, the summer's out of reach. Empty lake, empty streets, the sun goes down alone. I'm driving by your house, though you're not home. I can see you, your brown skin shining in the sun. You got your hair combed back and your sunglasses on, baby. I can tell you my love for you will still be strong after the boys of summer have gone. Hey, welcome you guys to this week, the day 3 of acids and bases. So thanks for hanging in there with me. And we're so close to the end of the year now. We'll probably do like 1 or 2 more lessons, just so you know. And well, have a great summer. Thanks for just being a part of my AP class, you guys. I really appreciate it, and I miss having an actual class with you guys. All right. So today we're going to be talking about equilibrium with acids and bases. And so we're going to see the return of K, our equilibrium constant. Okay. Couple of things. First is make sure you print or draw this chart out. That'll be really helpful, especially as we get towards the second half of this presentation. Okay. And this should be attached along with the PowerPoint or assignment. And make sure you have this. Okay. All right. You guys remember K, right? That's our equilibrium constant. Okay. Here's our equilibrium. Here's our equilibrium equation right here as a sample. Remember, it's products on top, reactants on the bottom, right? So we can apply this to lots of reactions, and we did this with solubility, right? And in this case, with the calcium carbonate, which is insoluble, our KSB is really small. That means that we're favoring the reactants, right? This one here, this is an equilibrium equation and for the production of ammonia. And if you notice, we have a really large K. So that means we're going to favor the right-hand side or the products of the reaction. All right. So when we have Ka, that's just a specific equilibrium constant that applies to dissociation of acids. Okay. So it's a constant that represents the strength of an acid in a solution, right? So when we have a strong acid, you notice here the one-way arrow, right? That means we favor the right-hand side, okay? So equilibrium's to the right. That means we have mostly products, right? So our K is going to be large, going to be greater than 10. We have a weak acid, though. What happens is equilibrium is to the left, okay? We favor the whole, not the dissociated acid, right? And so that means this, our reactants are going to outweigh, have more reactants than we will have product on top. So our K will be less than 1. So here's a couple of examples for you guys. All right. HCl, our strong acid, basically our K is 2 million, right? 2 times 10 to the 6th. Whereas our acetic acid, which we had on the last slide, is 4.9 times 10 to the negative 10th. So it much favors the reactants rather than the products. All right, same goes for bases, you guys. We just use Kb to demonstrate that we have a base. So the strong base, our Kb, is a large number. I really couldn't find a value for it because it's such a large number, it's almost infinite, right? And with the weak base, all right, if you notice, that's smaller than 1, right? So strong bases, the Kb is greater than 10. Weak bases, our Kb is less than 1. And the same goes for acids as well. Now, sometimes we do this, right? And we simplify things. And sometimes scientists have a habit of doing things that seem simpler to them, but complex to the rest of us. So anytime you see P whatever, like pH, that means negative log of H plus, of the concentration of H plus, right? If we say POH, that's the negative log of the concentration of hydroxide. So whenever you see P whatever, it's a negative log of whatever it follows P. So when you say pKa, we're taking the negative log of, let me go back to that. Sorry, you guys. Taking the negative log of Ka. Sorry, that P should not be there. Let's scribble that out. And same thing down here, you guys. If we're doing pKb, that is the negative log of Kb. Man, thought I went through this for typos. Guess I was wrong. All right, so keeping it moving along here. All right, often Ka and Kb are expressed as P's, right? As pKa and pKb. It's easier and it's shorter to write. That's what it comes down to. Okay, so when we have HCl, our Ka is 2 times 10 to the 6th, right? But if we make that into a pKa, it's negative 6.3. All right. If we have Ka for our hydrogen cyanide, right? Notice it's a very small number. If we make that a pKa, it becomes a 9.3. So what do you notice about these? Well, you notice the strong acid has a negative pKa, and the weak acid has a positive pKa. All right, so strong acids have negative pKa's and weak acids have positive pKa's. Same goes for pKb, right? Strong bases will have a negative pKb and weak bases will have a positive pKb. All right, so let's talk about the relationship between all this stuff, because that's what that flow chart is that I showed you right at the beginning of this presentation, right? So here's our base reaction going from left to right. Our Kb is 1.8 times 10 to the negative 5th because ammonia is a weak base, right? So its K is less than 1. And if we notice here, our pKb is positive, right? Okay. And right here, acid reaction, this is going the other way, right? We've just flipped the reaction around, and NH4 is a weak acid, right? So if we notice our Ka for that is 5.6 times 10 to the negative 10th, right? I just noticed another typo here. That should be an A. Our pKa then for this is 9.3. If you notice, they're both weak acids and weak bases, so they're both positive. And if you notice too, what happens if I add up 4.7 and 9.3? I get 14. Oh, sounds familiar. So pKa plus pKb gives us 14. All right. And if you took the time to type it into your calculator, you'd find that Kb times Ka is 1.0 times 10 to the negative 14th. There's that magic number, right? 14 when it has to do with acids and bases. Okay, so what's the big deal, Flugum? So the big deal is this. When we've got this chart here, everything is linked together. And if I need to, I can get all the way from pKb, so you can tell me what the pKb of a weak base is, and I can tell you up here through some calculations what the pH of that solution would be. All right. So how is this all linked, right? Remember, Ka times Kb is 1 times 10 to the 14th, right? If we look on the other side, pKa plus pKb is equal to 14. Okay, and then it's the same thing here going up and down, right? Remember, if we're going this way, it's the log. If we're going this way, it's 10 to the negative, right? Okay, now here's the tough part, the link between these guys here. And you have to use the ice chart, okay? I know it's your favorite thing in chemistry, the ice chart, but that's the deal, right? The ice chart, when we go from here to here, we have to use an ice chart, and I'll show you an example of that here in just a little bit. All right, so let's look at some problems here, you guys, with pKa and pKb. So here's the acid, right? pKb value associated with the conjugate base was found to be 15.5. Okay, cool. So it's positive. That means it's a weak base, right? So what's the pKa? Well, remember this, right? pKa plus pKb equals 14. So if this is 15.5, my pKa must be negative 1.5. That's simple, right? Everything's related. 14 is the magic number. Is the solution acidic or basic? I would say this, it's acidic, right? Because I have a negative pKa, right? That means that there's a strong acid, right? That the acid is dissociated, or most of it has. So then it says this, right? Is our conjugate base weaker or stronger base than water? It's weaker. Okay, that's because conjugate bases of strong acids are weak, right? And also this, right? Because we have this negative pKa, that means we are favoring the products in the reaction. Okay, so the conjugate base is going to be pretty weak. It's not going to accept protons as readily as water. All right, here's our last problem, you guys. And this is one where I'm going to show you that ice chart stuff. We want to find the pH of a 2.5 molar solution of hydrogen fluoride, and we know the pKa of this is 3.14. All right, cool. So we can do this if we know our, we want to find Ka, right? So to find Ka, we go 10 to the negative pKa. My Ka is 7.24 times 10 to the negative fourth. Okay, so that's step one. Step two is we're going to set up an ice chart. Okay, so here's my ice chart, right? We're starting with 2.5 molar hydrogen fluoride, 0 of these. I remember H plus and H3O are the same thing, right? F minus is the same thing. Okay, our change is going to be X. So here's our equilibrium values down here. Let's check out on the next slide how we use this. So how we use this is we use our equilibrium expression for the reaction right here. Okay, and we plug values into it. So I know my Ka is 7.24 times 10 to the negative fourth, right? I plug my values in from the ice chart for the concentrations. And remember this, you guys, we can ignore this guy down here, right? This X, okay, because it's so small, it's not going to affect the concentration very much. And when I do all that, I get H plus is equal to 0.0425 molar. Okay. If you have any questions about how to solve that, let me know. All right. Next, finally, we're going to find the pH. So the pH is the negative log of our concentration of H plus, right? So I take the negative log of my concentration that I just found here, and I get my pH is 1.37. All right, folks. So that's equilibrium and acids and bases. I just put together a assignment for you guys that has like 2 questions, okay? And those questions are multiple part, but that's all there is 2 questions. So, and again, if you got questions, come and message me, comment on things. I will get back to you as soon as I can, Monday through Friday. Okay, so take care, you guys, and I will see you around. Bye bye.